Good afternoon, everyone. Good afternoon, everyone. You're most welcome to day 5, which is our last day for this training at the moment. Let me say at the moment, we might be having some more additional training if you request so. So you're most welcome to the day 5 of our training on the advanced statistics and experimental design. It's brought to you and funded by the World Bank through the Center of Excellence in Agri-Food Systems and Nutrition in Eduardo Mondlane, Mozambique. So please, thank you so much for joining in on time once again. And we want to thank our facilitators for taking us through all these days and for being very patient with our slow learning and catching up with every person in the team. So thank you very much to our facilitators and the participants. Thank you to all of you who make it on time. So as usual, the registration link is being shared in the chat. Please ensure you register so that we capture your numbers, your phone numbers, so that we follow up on the training. So in our midst, we are lucky today, Professor Rogerio is with us. So let him, I'm going to give him a chance to have a word or two for us. Prof, thank you very much for joining in. Good afternoon.
Thank you, facilitator. Good afternoon, participants. Welcome to this last session, the 5th day of hard working and trying to learn about advanced statistics and experimental design. One thing I would like to request you is to provide us with 2 contacts. The World Bank, in its assessment, they want to contact the WhatsApp number, the one which uses WhatsApp, and the additional contact which can facilitate to contact you. So please provide us with 2 contacts, telephone numbers. With regard to the WhatsApp number, we are going to create a WhatsApp group so that it can facilitate us to communicate with you regarding this training and future training. So please provide us those contacts. The second request that I would like to leave to you is to, after the training, the World Bank or any agents hired by the World Bank will contact you to check more about what was the training. So please, when you see an email which will be coming with the World Bank, there will be an indication that it is related to the World Bank. So please respond to that email, because that will be really important to confirm that the training took place and you are involved in that training. So with this, I would like to wish you a wonderful session today, which is the last one. And again, thanking the facilitators and the referral for this collaboration, the process of delivering this session, this course on advanced statistics and experimental design. Thank you very much.
Thank you very much, Prof. Thank you so much. I think also just to let you know that there are 2 groups already, or WhatsApp groups, where the participants are in. So I'll ask my colleague to add you on those groups, because the 2 WhatsApp groups are already running. And the participants really engage a lot on those groups. Some of the facilitators are even part of the WhatsApp groups. Yes. Oh. So in case on the forms, on the registration link circulating, in case you are not able to put in the WhatsApp numbers, please ensure that you put the number where you can be reached directly, since the WhatsApp groups are already running. If there's provision for 2 numbers, please fill in all the 2 numbers. But most importantly, if you cannot fill the 2 contact details, fill the one you can be reached on directly for direct calls. So I think that's the only announcement. I know the certificates will pop up. We do know that you all did not get your certificates. Please bear with us. we are compiling to see who have missed the certificates for the first and second training. And we are also going to issue the certificates for this training. So please bear with us and put your learning first before the certificates. Let me say that, so that you concentrate on the training and not on the certificate at the moment, but they'll be issued. Thank you very much, Prof. Suzanne. Let me hand over to you and your team.
Okay. Thank you very much, Salma and Professor Rogario. We are so grateful again for another day of sharing our knowledge with the participants. We welcome you. Good afternoon. And would also like to inform you that in case anybody would like to invite us for our face-to-face training, since we have no restriction on travel, we can always travel if we are informed and we prepare on time and travel. We also encourage Professor Rogario to invite us to Mozambique so that we do a face-to-face with our postgraduate students there, but it will also be online so that other participants also can benefit. Thank you very much, and I invite Dr. Helen.
Professor.
Yes, Prof.
Professor, before, I really want your contacts because what you are saying is something that is in our plan. So please, I want to, yeah.
Yes.
So please, let's share the contacts.
Yes, I'm going to send you an email so that you get all our contacts, and then we keep in touch. Yes, thank you very much, Professor Rogario. Yes.
And
okay.
Prof, just a small one.
Yes.
Please fill the details in the registration link, not on the chat. Please fill in the registration link, not on the chat. And also the admins of the group, if anyone can put the WhatsApp groups, especially the one which is not yet full, the link, you can also post it here in the chat. Thank you.
Okay, thank you very much. And I hand over to Dr. Helen. Today, we are going to shift from experimental design. We are going to look a bit of survey so that people can get a feel of survey and how we can handle categorical data. Thank you very much. Over to you, Helen.
If you need to
hold on. Another thing is we are going to send out a short evaluation form. It is going to be in the monkey form. So we'll give you a few minutes before we close today. I encourage everybody online, the participants, please fill in those evaluation forms. They are good. They help us to make our training better for future purposes, for you and me. Thank you very much. Okay, bye-bye. Hand over to Helen.
Good afternoon, everyone. Okay, so what we're going to look at today, we're going to look at two things. One is you're going to look at analysis of categorical data. And then number two, we shall have an overview of sampling. So, but for now, we are going to start with the analysis of categorical data. Just to keep you posted, all the materials are within the week 2, day 5 folder. You can kindly check there and confirm. We posted the materials yesterday. So in case you haven't done so, please pick the folder. It has week 2, day 5. It has both the work on sampling and categorical. Okay. Let me check, let me confirm in the chat. Are there some people who got the materials already from the Google Drive? Just confirm to me in the chat. Okay, great. Thank you. So in case there are some other people who haven't, please do the same. Go in the Google Drive. The folder has week 2, day 5, sampling and categorical notes that we're going to use today. All right. So what we are having today, like I mentioned, we're going to go through analysis of categorical data. All right, maybe still I wanted to make it a participatory session such that we hear from each other. Sometimes when you're teaching online, you need to be very vigilant to know that the people that you have at the other end, they are with you. Can somebody type for me in the chat, when they talk about categorical data, what comes at the back of your mind? Just type a short sentence or 2 or 3 words. Okay. What is categorical data? Data with labels. Okay. Discrete data. Data that can be grouped, more than 2 points, non-numeric. Okay, qualitative groupings. Thank you. I'm glad that a percentage of us has a feel of what categorical data is all about. Now let's proceed on. We know that when it comes to statistics, it's we need to gather, organize, analyze, and then draw conclusions from the data. But what is most important is that before we go ahead to do the organizing and then the analyzing and drawing conclusions, we need to first get to know the nature of the variables that we are handling. Looking at what we are having here, I've got a snapshot of how an Excel sheet looks like, all data that has been collected. Okay, and in my columns, I've got the variable names, and then the rows gives me the characteristics that are picked, or attributes that are picked from each particular individual. Okay, and this individual could be a person, could be an animal, could be anything, you know, that has been that describes a data set. If just to take a little back, initially we had the previous data sets we're having, we had one that had diamond, whereby there are different variables and they are collected on different diamonds. So a variable is any attribute that takes different values for different individuals. Okay, for example, like I mentioned, if we are looking here, we have got type, and then under the type, our type is the variable, but can pick up wood, steel, wood, etc. And then when you also come to the design, it can also pick up, it has seed, invented, etc. When you look at speed, it also has different values that have been collected from various individuals. So after understanding how our data looks like, the different characteristics of our variables, then we can go ahead, do the analysis, and then draw conclusions. Okay. As far as categorical data is concerned, like some of you have echoed already in the chat, we are looking at categorical variables. We know what a variable is. A variable picks on different attributes, all right? And now a categorical variable, it's assigned labels, like some of you mentioned, that places individuals into particular groups. And then for the case of the quantitative, for a quantitative variable, it takes numerical values for which makes sense to find an average. Okay, sometimes even categorical variables could be termed as qualitative variables, because by the end of the day, some of them are just like words. A very quick example that we can take, for example, we can take our variable as marital status, and then marital status, we can have different levels like married, unmarried, divorced, etc. All right. In this particular example, if you want to, what we are having on a screen, for example, categorical variables, we have the time, we have also the design. Type has 2 levels, the wood and steel, and then design has seed and then invented. Whereas other variables that are numerical in nature, that we are seeing them here, they are quantitative variables. You can also think through other examples at the back of your mind, an example of a categorical variable. I remember at one point somebody was asking about, what about examples whereby we apply a Likert scale? For example, whereby you want maybe say disagree, strongly agree, neutral, and so on. Yeah, all those, when, for example, in case you're looking at attitude, okay, you can also look at that as a categorical variable. Okay, so here we are looking at an example that I'm portraying here, whereby it was just a random sample that was taken from 40 students. And there are different ways on how we can represent our data. But specifically today, we are looking at categorical data. And the question was, which would you prefer to be, okay? And there were 4 levels for the case of the preference: rich, happy, famous, and then healthy. So, and different data was collected. So it was collected from individuals, and then we go ahead and looking at the different levels that we are having from the preference, we can be able to tell that yes, it's a categorical variable. We also have another example here, and the question is that identify the individuals and variables in this data set that I'm showing down here, and classify each variable, whether it is a categorical or a quantitative. So can you type for me in the chat? Let's first, I can get like only 3 people or whoever is interested. When you look at this particular slide or the sheet that I'm showing, which one is categorical? Can you write down the categorical variables in the chat? We are just reminding ourselves. Okay, George is writing gender. Yes, state. Great. Somebody's writing birth. Is birth a categorical variable? We have state, grade, status, etc. Wonderful. I believe we've gotten that. And now let's type the one that are quantitative. Can we type the one that are quantitative in nature? Quantitative, we're having age, height, grade. Wonderful. Thank you. We've gotten that, so we can push on. And there are different ways on how you can really come up and summarize this kind of distribution. If you remember in high school, I don't know the different schools that we went to, most of the time whereby they would tell us to tally, you know, as you're counting, the moment you make a band of 5, then you put across, you know, and then you get to know that after that, you can easily count them very in a short time. But then also we can do a frequency table. Most of the time, if we want to represent categorical data, we use a frequency table, whereby now in this particular case, from the given example that we have up here, we are having data whereby it was categorical in nature. 40 students are sampled from the question that we saw on the previous slide, and somebody would just choose, you know, depending on the level. So you would just choose a preferred status. And coming here, you find that we've got 4 levels: famous, happy, healthy, and then rich. And then the frequency, these are the numbers. We have 7, 21, 4, 8, and then the total is what? The total is 40. So within the frequency table, after getting our frequency values, we can go ahead and calculate the relative frequency. And those are the different percentages that we can come up with. So with the famous, we know that our total is 40. So we are going to get, for each level, we divide by 40, and then we come up with those percentages. So what does that imply? By the end of the day, if we are presenting categorical data, most of the time, depending on the way that you want to present it, if you are using a table, you always have to quote the frequency at the same time the percentage. And then after that, you'll be able to explain and judge from the different levels, maybe which one takes up a bigger percentage compared to the other, depending on the narrative that you want to put across. But when we come to categorical variables, we make a frequency table, and then you put the frequency as well as the percentages, or you can do a visualization. And I believe that we've already looked at it, maybe, and also we're going to look at it more as we push on. All right. Now, yes, I was talking about how we display categorical data. We also have another example here. If you remember about the Titanic data set, within R, we have a Titanic data set. I don't know whether some of you know about this particular story, but among the different variables that was collected within the Titanic data was class, all right? And then class was categorical, whereby some people were in first class, second, third, and then the crew. These were their counts. And then we can, after, if this is a frequency table, which has got the counts, and then we can convert the counts to percentage. We come up, and then we come up with a relative frequency table. So having gotten the total, then we divide by each particular level to come up with a percentage. And then we get to know among the different classes that we have, which one had maybe, for example, more people. We are saying that the crew had 40%, 40.21%, then followed by the third and the first, and then the second class. Okay. Also, you can, we already seen that you can do, we can do bar graphs when it comes to categorical data. Sometimes we usually say that graph speaks, or a picture speaks louder than the figures to most people, and they can easily see it and follow. So you can also represent it as a pictorial. And in this particular case, we are still presenting what we had in the previous slide, the different classes, and then having the percentages on the y-axis, and then the class on the x-axis. And it's also good that in case you come up with a visualization or a picture of something, it is good that you always label it up. If you don't want to have it in the form of bar graphs, you can do, you can have a pie chart. I'm just going through this very briefly because at the back of my mind, we've been looking at these things throughout the last week and even within this particular week. Some other people, you can also do what we call a segmented bar graphs. They're also interesting. It's all about how you can present your data to be catching, and also it goes back to the audience, or what is your audience, or which people do you want to really show your data. And then are they within the academia? Are you presenting with a politician? Are you presenting at a conference? All these things really matter a lot, depending on the audience to which that you're going to present your data. So still with categorical, we can do segmented bar graphs, and this is how it looks like. We'll explain that already. Or you can do a side-by-side bar charts. All this shows that you really understand how, it helps you to understand how your data behaves. For example, in this particular case, it is still categorical. We plotted a distribution of phone, the type of phone somebody owns in respect to the different age categories. We can see for the case of iPhone, the brown one is 18 to 34 as per the scale. The yellows, those are between 35 and 54. And then the green is for the 55 plus and above. Okay. Now, let's move on and also talk about, given that now we know what a categorical data is, we know how you can represent it. And then at the same time, we've also looked at how it can be, how can you represent it in case in a visual form. If you want to create a pictorial, you can do bar graphs, and then you can do pie charts or segmented graphs, depending. Of course, it goes back also, remember, on the levels that a particular variable has. When we talk about categorical data, we cannot miss to talk about the concept of cross-tabulation, or sometimes it's referred to as a contingency table, whereby in this particular case, you're considering two categorical variables. If you remember very well, when we are looking at data manipulation of the various data that we have, we mentioned that in case you're having two categorical variables, for you to check the relationship, you can go ahead and do what? You can go ahead and do a cross-tabulation, and then in the process, you can check whether the two variables are independent. I don't want to preempt that. We're going to look at it as we push on. Now, looking at this, we've got a cross-tabulation, whereby we've got two variables. We have the one for the groups where we have group 1, group 2, group 3, and then we have the one which has the termites, either attached by termite or not attached by the termite. Those are two. We've got one group has 2 levels, then the other variable has 3 levels. So what we are seeing here inside here, these are just distributions. That those attached by termites in group 1 are 193, attached by termites in group 2 are 148, in group 3 there are 210, and then the subtotals we are having here, we sum from 193, 148 to 110, and we come up with 551. Of course, we need to know this particular background, but when we get to R, it's just a command that we're going to write, and then we'll be able to see how all these contingency tables look like. But sometimes it is important to have the background of what really the computer is going to give you. Now, when you come to the not attached termites in group 1, we have 307 as the count. Then in group 2, it is 352, group 3, it is 290, and when you sum them up, you come up with 949. Okay, so we sum row-wise, the first group, which is 551, and then the second group, which is 949. Those are the subtotals. These are the totals for the case of the termites, the two groups. And then we also have where in the other group, which has got 3 groups, group 1, 2, and 3, and the group 1, those that are attacked by the termites, 193, and then the ones that don't, we have 307. So when you sum now column-wise, the subtotals are 500. In all the 3 groups, they are 500. And in total, our N is 1,500. So what you're seeing here, when you're seeing a distribution of 2 categorical variables, and we've got 2 rows and 3 columns. So in this particular case, we have a 2 by 3 contingency table. Okay, let me first check in the chat if we're in the same page. Okay. Are we on the same page? We can't. Okay, I'm going to reduce the speed. Sorry about that. Okay. Speed too much, please. Okay, I'm going to reduce the speed such that we all follow very well. But at least I've seen you've typed yes, implying that we are still together. Okay. Let's move on. So, okay, let's go slowly on this particular slide so that we are together. Remember on the previous slide, we saw what cross tabulation, or some other people refer to it as a contingency table. And these particular tables, depending, like I mentioned on the levels, you find that when one variable has 2 levels and the other one has 3 levels, when you do a cross tabulation, you'll come up with a 2 times 3. In case one is of 2 levels and the other one is of 2 levels, then you'll come up with a contingency table of a 2 by 2. So when we come to these particular tables, the contingency table, we can have an N times M ways on how you can create contingency tables, but it still goes back on it is being defined with the what? With the levels. Now I want to talk about two-way tables, okay, and marginal distributions. We've already looked at this particular concept. I remember when Professor Susan was explaining about exploratory data analysis, but now let's get more detailed. What happens in case of categorical? So we are saying that when a data set involves 2 variables, what do we begin with? Most of the time, we begin by examining the counts. How are they distributed within these particular groups? If you don't want after the counts, you can as well go ahead and get the percentages in each of the categories within that particular variable. Okay. So a two-way table, what comes to your mind when you say about a two-way table? This one describes 2 categorical variables. Okay, 2 categorical variables, whereby we've got the counts according to the rows, and then the what, and then the columns. Now, let's take this particular example, what we are having here. We are having two variables, two categorical variables. One is gender, where we have a female and then male. And then the other one is, they are asking that the chances of getting rich among the youth. Chances of getting rich is categorical, and it has almost no chance, that is one level, some chance, but probably not, that's another level, a 50-50 chance, a good chance, and almost certain. So in other words, getting rich, chance of getting rich variable has got 5 levels. If we are to count 1, 2, 3, 4, 5. And now, then for the case of the female and then the male, that is what? That is gender. So we are doing a two-way table of to check how the counts are distributed within the levels. Looking at this particular table, we see that among the females, there are 96 females that said that almost they're seeing no chance of getting rich, but the males are 98. These are just counts. And now when you total up 96 plus 98, we come up with 194. This is the total that we get of those who said almost no chance with irrespective of gender. Okay, this is our 194. In case you put in, you divide the female and the males, we are seeing that of the 194, we have 96 males and 96 females, sorry, and 98 males. Okay, when we come for the case of almost certain, we are seeing that the females are 486 and then the males are 597. When you total them together, we are having 1083. So what you're seeing here, the total here, these are, they sum up, or for example, with the females and then the males. So the total count of those who said of not getting rich are what we are having here: 194, 712, 1416, etc. And now, that is if you're looking at it row-wise, for the category of getting rich. And these particular totals, as we move ahead, these are referred to as marginal distributions. Okay, the 194, 712, 1416, and 1083 are marginal distributions. They're distributed in respect to gender. Okay, and now what about in case we consider gender itself? Among gender, we have the females and then the males, and they're also distributed according to the chance of getting rich within the different levels. So the different, when we sum up here, the different total that we get, the 2369, these are the total females being distributed among this, the variable of chance of getting rich. And then 2459, it is the total count for the males that within the variable of getting rich. Okay, so here looking at these particular totals on your right, they are marginal distributions for somebody getting rich, and then the marginal distributions for gender are the ones that the total count for the column wise. Okay, so you can ask yourself a question that how many young adults we are surveyed. So the adults that we are surveyed in total, they are 4,826. In this particular question, what are the variables described by this two-way table? The variables are 2, gender, and then chances of getting rich. Okay, I think there we are okay. This is just a more illustration how we can get the marginal distribution, which I've already explained earlier. So just to take a close look, we are in this particular case, we are having two variables that are categorical. One is gender, which has got female and male, and then the other one is job category. So for us to come up with the marginal distributions for the job category, we take the totals, the marginal, okay, the marginal totals that we are having here. And then for the case of the marginal distribution for gender, we take the totals that are being summed column wise. So we'll have the margin distribution for gender. The totals that are being summed row wise are the marginal distribution for job category. Okay, hope that is very clear. And then also the other thing, maybe it's about the conditional distribution. We also, you know, within when you're looking at categorical data, you can be able to know, okay, what is, for example, the percentage of female in this particular case that have got clerical jobs, given that there are 363 clerical jobs. So it is just from here, we are just getting the totals that we are having. And then when you push on to the second, we are moving on to calculate the percentages for each particular cell. So given what we are having, somebody, you can be able, from the different the percentages within a cell, you can be able to come up with a conclusion and then also, you know, make comments, because most of the time, when we are explaining data, you look at the main key result, what has been so interesting, and also it goes back on the objective that you want to achieve. Okay, so just to take a little bit, when we come to the females that did the clerical, in this particular case, it is 206. We are dividing by the marginal total of those within the clerical job. Then with the custodial, it is 0/27. The 27, if you remember very well, is our marginal total we are getting for those that are dealing that have got custodial jobs. All right. Okay. Okay. Now, yes, I've already talked about we're still under the two-way tables and marginal distributions. These ones I've explained. So we are looking at the counts within the distribution of the within the respective cells. Okay. And sometimes people prefer to have percentages because they are most of the time more informative than the counts. And we've seen how you can quickly calculate them. But as we move on to R, you'll find that it's very easy on how to calculate percentages within a cross tabulation, because you just need to know what command you really have to use. By the back of your mind, now you need to know what are the marginal distributions. We are saying that these are just the different totals within a respective category by their distribution. So at the same time, you can also make a graph to display the marginal distribution, depending on what kind of graph that you want. Okay. All right. Going back to our example that we had earlier, which I showed you about looking at gender and then the chances of getting rich. How do we examine the marginal distribution of chance of getting rich? It's the same as the one that we've looked at for the categorical, for the job category and gender. On this one, we've already seen our different totals. So after from that particular table above, we can move on further and convert it to what? To percentages. Here, if you're considering the marginal distribution, all our totals without, in case we don't want to separate according to gender. So it implies that we are going to get our totals, for example, almost no chance. When you run the frequency, okay, the usual frequency that we know, we are coming up with 194, and the total is 4,820 and 26. So these are the percentages that we are coming up with the marginal distribution. And you can still quickly do a bar chart and plot and see to give you a more clearer view on what you want to talk about. So you can represent this particular variable, one in form of a table or in form of a chart. And it still goes back to you on what audience or how do you want the people representing that your work to understand it very well. Okay. Now, so in case you want to look at the relationship between two variables, I've already mentioned about the conditional distributions. For example, in the previous one where we are looking at the chances of somebody becoming rich, given the different levels. So you can condition that we can say, well, for those who say that if what will be the chance for a female to become rich, given that the total, they given a particular total. We know a total, but we want to come up with a particular percentage of a given soil. So what do we do? Number one, we select the columns or the rows of interest. That is very important. And now you go ahead to use the data in the table to calculate conditional distribution, the percentages. And after that, you can display them on a graph. You can do a segmented bar graph, you can do a pie chart, or you can do bar graphs, or you can go ahead and use a side-by-side bar graphs like we explained earlier for compulsions. Okay. So initially, what we saw earlier, if I go back briefly, in this particular case, here we are looking at marginal distributions, considering all our totals, irrespective of the division, for example, the case of gender where we have males and female. So we are taking our if you're drawing just a usual frequency table, we have the frequency and then the percentages, those are the marginal distributions that you're having. And then if you want to go ahead and now look at it with respect to the different levels, then in that case, we are looking at condition distribution. Now, in this particular case, for example, we are looking at, we are considering males. Remember our, this particular shot that we have. The total males are 2,459. So for us to come up with a conditional distribution, for example, at almost no chance, so it's going to be 98, we divide by the total what? By the total males, which is 2,459. The same applies to all the rest. It's what we are having here. So we are having, they're trying to explain the relationship between gender, and in this particular case, we are considering males in response to the chances of getting rich. After doing this, you can also go ahead and do for the case of what? For the case of the females. We know that the total for the females from our screen are 2,367, and you can be able to, what is the percentage of a female to have a chance, some chance of getting rich, given that the total is 2,367. So we go ahead and compute our percentages. So whatever that we are having now in our particular table, they're just conditioned, they are conditioned distributions. Okay. All right. Okay, so here we are. You can also go ahead and you can also, after having your distributions in this particular case, you can represent them in pictorial form. All these are just different ways on how you can present categorical data and check the relationship between two categorical variables. So from here, we can see the males and then the females, and then the opinions are being colored. For example, in this particular case, the yellow, 50 to 50 chance, you can easily see that. And then the red, we have a good chance, among others. And still within R, you can just write one command and you can come up with all these particular results. But it's good to have what they are talking about. So sometimes just a diagram or the marginal distribution and the condition distributions might not really give you a feel of what conclusion can we see among these two variables. So, but we are going to see, how do you come up with a conclusion if there is a relationship between these two categorical variables? We are going to look for, at this particular stage, we are not going to look at it, but we are going to look at it as we move on. And it's also, I would also encourage you that sometimes you can't say that there is a strong association between two categorical variables, but they could be, there's also some other factors that might be influencing those variables to be like that. Okay. So in summary, what have we looked at so far in case we want to make sense of categorical variables or categorical data? Number one, we can display categorical data with a bar graph. You can use a pie chart. You can use a segmented bar graph. You can go ahead and calculate and display the marginal distributions of categorical variables from a two-way table, like we've seen. After that, you can go ahead and calculate and display the conditional distributions as per the previous slides. And then after that, you move on to describe the association between the two categorical variables. Okay, let me check in the chat. Are we on the same page? Are we on the same page? Okay. Sure. All right. Okay. Thank you. Thanks for the replies. There are many. Now, like on the previous slide, if I take you back briefly, we mentioned that here, there is a point that we are seeing a relationship between chances of becoming wealthy or becoming rich, and gender. These are two categorical variables. But we are wondering, yes, we are seeing how they are categorized, and we are seeing our picture. But the question is, can we come up with a conclusion? Can we test that there is a strong association between these two variables? So how do we do that in R? If you remember, within our data management, where we are seeing the method of analysis and then the method of visualization. So when you're having two categorical variables, for you to check if there is an association or if there is an association between these two categorical variables, we have to do what we call a test of independency. And so it is now the concept that we are going to look at. Okay. Maybe before we move on to see the test of independency, can you type for me in the chat what comes at the back of your mind when they tell you that, well, for you to test an association between two categorical values, you need to test for independency? What does it mean? Type for me in the chat. Okay, somebody's saying it means that you use a chi-square. Great. Chi-square and then a t-test, compulsion, chi-square test. Can I see more? No relation. You have to find a chi-square test. We are testing for relation. Okay, to check whether we have no dependency instead of no independency. Okay, we are testing. Somebody has typed, you can use a fish exact test and hypothesis. All right, thank you. I believe that Yes, Annette, you're going to be answered anytime. Okay, so when in case we want to make a conclusion, to check if there is a relationship or an association between two categorical values, we do what we test for independency. And how do we do that? Like most of you have commented in the chat, we use a chi-square test. So a chi-square test is a test that that is used to test for independency between two categorical values, variables, okay? And we are going to go ahead and test it. So the null hypothesis would be there is no association between two categorical variables. And then the alternative is there is an association. When they say within the null, there is no association, or somebody could say there is no independency. And then the alternative is there is independency. Remember, if we just go back a little bit within probability, when we talk about independency, it implies that when you're looking at two particular events when they are independent, it implies that the occurrence of one does not influence the occurrence of what? The occurrence of the other. Okay. Now here, when we are looking at two categorical variables, all the time, if you want to test if there is a relationship, you do what we call a chi-square test. Of course, there are some scenarios when you're calculating a chi-square, and maybe when you're running it within R and it fails, that's when the concept of using the Fisher exact test comes in. Somebody commented it within the chat. Okay, and also within when we are looking at a chi-square, when a chi-square test, there is also what we call expected values. Remember, what we see within, for example, the Excel sheet or the collected data, that is the observed, okay? But then, well, what about the expected? Remember, all of this particular week they have been sharing about experimental data, and then we've got experimental error, then sampling error. We believe that still when this particular data is corrected, there is an error. We cannot be 100% right that that we've got all things right. So we're also going to calculate the expected values. All the things that I'm talking about, they lead us to how a chi-square statistical test looks like. We've talked about when it comes to expected values, we get the row totals. Those are the marginal totals times the column totals divided by the grand total. All right. Maybe to take you back, I talked about the marginal rows and then the marginal columns. They are the ones they're referring to us here. And then we divide by our total. Okay, but it's important at the back of your mind to know what are you testing? Okay, how do you set the null and how do you set the alternative? It is very important because as we push on, it's the one that directs you either to say that you reject H naught or you fail to reject H naught. Okay, let's move on. Now, when we talked about, remember within the chi-square, it is being governed by two things. We've got the observed frequencies, okay, what we pick from our data, and then we also have the expected frequencies. And in this particular case, I've already talked about marginal probabilities, whereby you multiply the product of the marginal, okay, and then the marginal totals times the column totals divided by the total number of observations. And within R, that could be done very perfect well. After that, we get the difference between the observed and the expected frequencies. Still within the software that we are going to see, all these things are going to be calculated automatically. But sometimes it is good for us to know the feel of how these things come about. After step 3 of getting the difference between the observed frequency and the expected, then now the next step is for us to calculate the chi-square test, the value that we are going to check. What value do we have? Okay, let me first pause a little bit. I check in the chat. Hope I've not left anyone. Okay. In case, I also want to encourage you, please, if you have questions, you can type them in a Q&A. My colleagues will be happy to answer those various questions. And then the ones that I see that quickly to see, I'll be able also to answer them up. Okay, so when you check in many statistical textbooks, or even if you Google at internet, all right, a chi-square test statistics, we are saying that it tests for association, or it's a test for independency, or somebody can say it is a test of association. With the NAR, we mentioned there is no association, and then the alternative, there is an association. When you check in most of the books, this is how the chi-square statistical test looks like, okay? And so we have the OI, we get the observed frequency minus the expected frequency, the diversion, it is the difference, or you can call it the deviation, and then everything is squared, we divide by the expected frequency. And you can also use chi-square tables. You know, within different statistical tables, you've got chi-square tests, and we can read off the rows and then the number of rows. We can also look at the number of columns, and these ones help us to come up with the degrees and the different degrees of freedom. So you need to know when you're looking at your contingency table, how many rows do you have, how many columns do you have. So when you multiply the rows minus 1, then times the C minus 1, it gives you the degrees of freedom. When you check in different statistical tests, we've got chi-square tables. So you can look at these particular values from the table that you'll get, or you can calculate them and then compare. And then you can also use a p-value to compare if there is an association. But we're going to look at that. All right. Just to echo again, within the chi-square statistics, what do? We compare the observed values to the expected values. Remember, the observed, this is what you collect within your data. We're going to see it in R, and I'll still emphasize it more. And then in case you do the computation, what are the would-be expected values? So we are comparing both of them. And then the moment we are trying, after that, you're trying to check if the difference between the observed and the expected are statistically significant. And sometimes you'll find that if you're checking the difference between the observed and the expected, when, for example, you might find that you come up with a very low value for a chi-square, whereby that implies that the difference between these two, the observed and the expected, is really, really small. And then sometimes if you've come across it, that you can calculate, and also you see that the chi-square, it gives you a 0. And what should come at the back of your mind is that in that particular case, the observed values are equal to the expected values. And so all this particular information, as we are going to go ahead and check how to compute the association using a chi-square test, all this should come at the back of our mind in the different respective figures that we are going to come up with. So in general, what is the summary before we move on to the calculation? Rule number 1, you need to know the two variables that you want to check. Okay, and then what are the two variables? The two variables have to be both categorical in nature. You set your hypothesis, the NAR, no association or no independency, and then the alternative is there is an association or there is independency. In case we do most of when you're going to use statistical softwares, in this case, which is R, you can set your significance level. You can set it at 1%, at 5%, etc. But the key rule is that when the chi-square table value, I've talked about the tables that we've got statistical chi-square tables. Sometimes they're referred to as critical values. If it is less than the calculated, calculated, implying that you can go, you can do the calculation of a chi-square manually from like what I explained earlier, having the observed and then getting the would be expected frequency. You square the deviation, then you divide. That will give you a chi-square that is calculated. But most of the time, if what you read from the table is less than what you've calculated, by the rule of thumb, we reject the H0. The moment we reject the H0, it implies that now we are going into the alternative and we conclude that the categorical variables are independent. Okay, let me first check in the chart. Okay. No independency, no association. All right. Now, we are going to just take this particular example. I would just pick from a different textbook, whereby what we are having here, we want to check, is there an association between a city, in this particular case, which is the area, and the offense. What we are having here is that we have got area A, B, and then C. And then these are the respective offenses that we have: burglary, robbery, car theft. The totals, what we are having here in the rows, the total rows, these are our marginal distributions. For A, it is 55, for B, it is 49, and then for C, it is 46, right? And then if we are to look at the distributions for the offense, for burglary, we have 50, robbery, they are 60, and then car theft, they are 40. Now, let's go ahead. What we are seeing here, these are just observed frequencies, or what, I mean, those are the counts that are being shown from the data that you can get them. And what we are seeing here, these are, we can say it is a 3x3 contingency table. It is just a cross tabulation between area and then the type of offense. So what are we going to do next here? We need to go ahead and come up with the expected frequencies. We get the difference between the observed and the expected. We square them, then we divide by what? By the total sum to come up with a chi-square. Okay, so number one, I know, like I mentioned, two variables that I'm having here, they are both categorical. So I go ahead and set the hypotheses, H1, H0, and then H1. Okay, with H0, I'm saying there's no association between offenses, and then the area of the city, and then the alternative is that there is an association. Okay, so I'm not going to go into the different calculations of how the things came about, but in case you check in the notes, you can easily follow. You can easily follow through and check how the different results came about. You can easily check through on your own and look at that. So what we are having is that at the end of the day, for example, where we have A here, we are having the sums of the different rows and then the columns. So we have OI minus E, observed 1, observed expected 1 squared divided by E1. These are the values that we're having down here. So what we are going to do, we are going to go ahead and sum them up, and everything will be divided by 150 as the total. So here, the values were substituted within the test statistics, and we came up with 23.13. All right, this is the value that has been calculated. So the calculated value is 23.13. Remember, if we go back briefly, we are having, each variable has got 3 levels. So for us to come up with the degrees of freedom, we get, so it is a 3x3. We are going to have the number of rows minus 1 and then the number of columns minus 1. So that's how we are coming up with the 4 degrees of freedom. In case we take our level of significance as 0.05, okay? And so if you check in any statistical table, like here we are saying that when you read, you come up with 9.488. What conclusion would you come up with? We are having that the calculated is 23.13. When you read from the table, it is 9.488. What conclusion can we come up with? Can you type the answer in the chat? What conclusion can you come up with? Okay. Wilfred is saying that we reject H naught. Reject H naught. Kenneth agrees also. There is Ismail, we reject. Okay, so it's less than the calculated, hence we reject. No association, so reject H naught. There is no independency. Okay, fail to reject H naught. Okay. So remember, if I take you back from our conclusion, we said that if the calculated value, if the critical value, that is the table value, is less than the calculated, we reject H naught. Okay, now let's go back and then we mark ourselves if we are right. We are having that from the table, it is 9.488, which is this is from the table. And what is calculated is 23.13. So in this particular case, we reject H naught, since what is read from the critical value is less than the calculated. Okay, so the first one was when your alpha was 0.05. What about in case we use 1% significance level? If we use 1% significance level, we are told that the critical value is 13.28. Then what do we do in this particular case? Looking at 1% significance level, the value from the table, the critical value is 13.28. What do we do again still in this particular case? And then we are going to come up with a conclusion together. What will you do? Okay, still they're saying that we reject H naught. We still reject. Thank you. It is still less than the calculated, the same etc. So in this particular case, I'll concur with you. So what we'll do, we will conclude, we'll reject H naught and say that the test is highly significant. So in this case, we can conclude and say that there's strong evidence of association between the two factors. In other words, the two categorical values are independent. Okay, let me check in the chat. Are we on the same page? Hmm? No independence. Hmm? No association. Oh. Okay. Yeah, when there is no association, there is no independence.
Or non-independence, yeah, that you become independent.
Oh. Okay. Okay. So In case we move to R, we are going to see how we can present categorical variables. So what we can do, we've already seen how factor variables look like. Within the factor variables, that is what I refer to them as the categorical ones. We have to convert them to factor. We create frequency tables, and then later we'll use the table function. From the table function, we'll be able to calculate the proportions using the prop.table function. And then we can also get the marginal frequencies using the margin.table in brackets. And then inside we can put our command, what we want to look at. So this particular, what I'm showing here, we have n, which is equal to, let's assume that our n is equal to 500. And what I'm having, I want to create a data frame. I've got my A, I assign it. We are going to see this within R. I assign it as a factor. I create a sample which has A1 and then A2. This is just an imagined data set that I'm creating. Okay, and I put C. I need to have them together. Then I already know what my N is, rep equal to true. So implying that when I come to A, my A1 and A2 are going to be replicated 500 times. The same applies to B. I want to create a factor variable, and it's within a sample where I'm going to have B1 and B2. My N is still 500, and then REP replicate 500. The same applies to C. And then I can create a data frame or a data set that has got A, B, and then C. I will attach my data set depending on the objective name that I've given it. And then using the table command, I can put in whatever variables that I think I put in the first variable, in this particular case, which is A and then B. And this is going to be our output. I think this will make more sense if we do it directly within R. Okay, and then also we can do the margin.table. For example, in case if we want to get the marginal distribution, one, that will be for the first variable that you're considering, and it will be summed over B, which will have the F frequencies. And then we can also sum it over the other variable. We are going to demonstrate that when you take the prop.table, in that particular case, we will be getting the percentage with the cell percentages. Okay, in case you have the prop.table and you put in the name of your data set and then you put (1), it implies that now in that particular case you're getting row percentages. If you don't put anything inside the command, you're getting the cell percentages within each particular cell. If you put 2, we are going to see this in R. It implies that you're going to come up with column percentages that you're going to come up with, because remember we have the rows and then we have the columns. Okay, all right. So now that we are going to use R, sometimes, for example, you might not be able to do it manually, and you're going to use a statistical package. So what conclusion can you come up with? It all goes back to the p-value. How do you interpret a p-value? And then a chi-square test, such that you're able to come up with a conclusion and say that there is a relationship that exists between the two categorical variables that you're considering. So we are going to see this in R, and then we come up with the different conclusions. All right. So this was the theory bit. Now we are going to move on to the analysis of categorical data in R, so that we see what we've been sharing. How do you do it in R in a very simple way? Okay. I encourage you to go to the folder. We are going to use categorical data.r is what we are going to use within that particular folder. Okay, so I'm going to stop sharing this. And then I share the category, I share my R, open your R on your computers. Okay. Okay, we are going to use a script, categorical data.r. It's what we are going to use. It is also one of the scripts that we sent in the materials of week 2, day 5. Okay. How about a Fisher test? You will use a Fisher test if you're using a chi-square and you come up with an error. Most of the time, the rule we have to say that the counts within if you check the counts within the cells, if it is less than 5, there are high chances that as you compute the chi-square, you're going to come up with an error. So the moment you're using a chi-square and you get an error, that should be an indicator to ring for you that the chi-square, in this case, it will not work. So let me go in and use a Fisher exact test. Which folder? We are using week 2, day 5 sampling and categorical folder within the Google link. Okay, somebody's asking, how about SPSS users? We are not looking at SPSS now. We want to see how do we do it in R. Okay, can you confirm to me if you've opened your R scripts? How do you load the data? That was one of our first lessons. Okay, okay. Can we open the categorical data.r script? Okay, it's what we are going to use. And then inside still that same folder, there is, somebody's asking, can I use starter? Of course, why not? Depending on the statistical software that you're using, you can still go ahead and do cross-tabulation. All right, so can we continue? Can you if you've opened your categorical data.r script, can we continue? Type yes if it is okay. Okay. All right. So what we are going to start with now, we want to see how do we do the analysis. There are 2 examples within this particular script. There is this first one, which I told you that it's just, we've just created it. And then the other example we are going to use, it's the one that has a data set, and the data set which has got work salaries, the CSV. But we are going to look at that. We are going to have these 2 examples, and then we check how do we do that. Okay, we've already said that the moment you open your, let me ask in the chat, are you seeing my R script? Have I shared? Can you type 1? Okay. All right. So, what we do, we first run our libraries all the time. If you open an R script, you first run your libraries, and if they run successfully, then it implies that you're good to go. Most of the time, sometimes we come up with errors that maybe a certain function is not found, as we've been seeing that throughout this particular week. It implies that maybe there is a package that you needed to load, or to run, but you didn't. Okay, now let's take line 13. I'm saying that I want to create 500 observations. That is my N. You can change it to anything that you want. I'm just giving an example. You can change it to 10, you can change it to 5, you can change it to anything. So in case I run line 13 and I check in the R console, it has been noted. Okay, I want to create my first variable, which is A. Okay, remember, when it is a factor, you're letting R that you want to create a categorical variable. And I'm creating a sample. I'm putting everything inside the sample, which has A1 and A2. A1 and A2, these are my levels that are under variable A. Okay, and I'm telling my N, these are the number of observations that I want for A, and then I want them to be replicated 500 times. REP, that is replicate, which is equal to true. So in case I run that particular line, line 14, okay, so you find that when you check in the environment, it is showing you that it is a factor with 2 levels, with A1 and A2. Okay, I can do the same for B, variable B. It's the same explanation, only that this time I've got B1 and B2. I can also run that line, and then I also run line 16, which is still the same. When you check in the environment, it is still telling me that C is a factor with 2 levels, which has C1 and C2. B is a categorical, a factor variable with 2 levels, B1 and B2, and then the same applies to A. So now, what I want now is create a data set, which I've given a name called my data. Okay, that is the object name, which I've given my data. You can change it to anything that you want in case you don't want to use my data. And then I'm like, okay, I want to create a data frame. Remember when we talked about a data frame, whereby you want to create a data set. And inside a data frame, I put my first variable A, my second variable B, and then my third variable C, and I put them together inside the data.frame. So if I run line 81, what is going to happen? If I run line 18 and I look in my environment, you find that now it is showing me that I've gotten a data set which has got 500 observations and 3 variables. You can click on the Excel icon and also have a look on how these variables look like. We are seeing that with A, it has A1 and A2 levels, B, B1 and B2, and then the same applies to C. But remember, this is just an example that we've created. After this, we can look at now a real example. Let me check in the chat whether we're on the same page. Are we together? Okay. Great. Okay. We've also been talking about attaching your data set. So we are having variables A, B, and then C. Just to remind you, in case maybe you get stuck on something that is not so clear with you when you're doing it in R, what you do, you use a help command. You type question mark, and then you after the question mark, you write something that you want to get more details about. Okay, now I know at this particular stage, my data set, my data set is called my data. Okay, so if I want to do and I've got 3 variables, A, B, and C. If I want to create a cross tabulation or create a contingency table between two variables. For example, if you remember what we said, you write table and then inside you put the first variable and then the what? The second variable. So in case I run line 26, if I go and run it, I expect to see my results in what? My results in the R console. Okay, so we are having A and then we are having B. Those that in A1 represented within B are 121. We are seeing the different counts, and since it's a two level, each variable has got two levels, so we come up with a 2 by 2 contingency table or a cross tabulation. All right. So in case you can also put line 26 into an object which I've called my table. If I write my table and I say, let it be equal to line 26, I'll still come up with similar result. I run that particular line, and then for me to see the output, I run the object and I still come up with similar results. We are going to see it when you're running a data set itself, such that it makes more sense and even us to pick it very well. Okay, we talked about the margins. So in case you want to, these are just the sum. Okay, if you want to create the margins, margin.table, and inside you put the name of my previous output, which is the contingency table for A and then B. In case inside I put a 1, it implies that I'm going to come up with the total frequencies of A. Okay, if I run that particular line, you can come and check in the console that remember, it's a matrix form, row by column. So my row in this case, it's 1, and it's being represented, it has got the A. So what R has done, it is summed over 1 to 1 plus 1 to 5. So we come up with a 246, and then the 1 to 7 plus 1 to 7. That's how we are coming up with a 254. Okay. You can also change, and instead of 1, you put 2. In this particular case, they will be summed over the frequencies, the frequencies for the case of what? For the case of the B variable. So when you run that, this is the output that you will get. If you check, if you go back with your output, so it is being summed now, you get 1 to 1 plus 1 to 7, and then 1 to 5 plus 1 to 7. So we come up with the total marginals on both on the column end and then the row end. Okay. In case we just want to come up with the proportions of the different counts, we use what we call the prop.table. So that is our command that we use. And then inside you put your object name. And my object name, I used my table. So in case I run this, it's going to give me the cell percentages of what I explained earlier within the PowerPoint. So in case I run that, these are the proportions that we get in the respective cells. You can go ahead and multiply them by 100 and check. By within R, remember we talked about manipulation. You can go ahead and then multiply them by 100. At the same time, you can also round them off. Okay, what we've done up there, for us to come up with raw percentages, what we do here, we came up with the cell percentages. All right. Now, in case you want to come up with raw percentages, you go inside the prop.table command and then you put a 1. If you want to come up with column percentages, instead of a 1, you put 2. Okay, so in case you run this particular, run line 45, we are going to come up with the raw percentages. Okay, and then if you want to come up with the column percentages, instead of 1, you change and then you put to a what? You change and you put to a 2. And that is the output that we are going to come up with. I'm not going to try in line 57. It will not make sense now. So what I want us to do is now to do it on our data. Can you go and import the data set which has work salaries? Let's repeat whatever that we've done up here using work salaries, and then we do more clear interpretation basing on the data set that we have. Okay. Okay. Let's import the work salaries.csv dataset. Within this dataset, maybe as you said, the working directorate, we have got different variables. We have the rank, we have the discipline, years since PhD. These are the variables I'm reading out. We have the years.service, we have the sex, we have the salary. Maybe I can first stop sharing and then I share it and we see it together. This is the data set I'm talking about that we want to import in R, the work salaries data set. It has the rank. Rank is a categorical variable with different levels. We have professors, assistant professor, and then assistant and then associate. All right. We have another variable which is discipline, and it has got 2 levels, B and A. B, that is humanities, and then A, sciences. We have years since PhD. This is just quantitative. They're just number of years. We have then years since service, since somebody is employed, the time that has been spent. We've got sex. This is gender, either somebody is a male or female, and then we also have salary. So this is the data set I want you to import in R, and it's the one that we are going to use. Okay. Okay. Now, let's go back briefly. Let's go back to line 28. As then we'll move to the other section. I created the my data object, and inside the my data object, I wanted to create a table, a cross tabulation for variable A and then variable B. Remember, here our A, they are the rows, and then the B are the columns. All right. So in case I run if I run line 28, I will not be able to see my output. If I run now the object itself, the my table, I come up with the counts inside in variable A. Those that when you're looking at the counts in A1 and they're also in B1, they are 121. then in A1, and also belong to the B2 category, they are 125. If you come again to A2, we are having those in A, the ones that belong to level 2, but they also in B1, they are 127, and so on. A2 and then B2, they are 127. Now, when we talk about if you've got 121 and then 125, 127 and then 127, this is a 2 by 2. Remember when we talked about the margin table, we are trying to get the sum. Okay, we are going to get the sum of the rows in case you put 1 here. So it implies that we are going to have is going to be, if you put 1, remember our rows are the rows are the A's. So it is going to sum for us the A's. So if you run this particular line here, line 32, you find that, so it is, if you look in the console where I have highlighted, it gives us the marginal or the sum totals for level A1, which in that particular case is 246. Okay. And then for A2, it's going to go ahead and sum 127, 127, which will be 254. 254. And these are the marginal totals for A, giving us for the levels of A1 and then A2. Now, in case you replace, instead of having 1 and you put 2, so now it is going to sum column-wise. So we are going to come up with the total margins for the case of B. If you run line number 2, what it's going to do, if you look in the console, now it is in my table output, it's going to get 121, and then it sums it with 127. That is the first column in the B1. And then in the B2, it is going to get 125 plus 127. So for us to see that marginal output, we use the margin dot table, that is line 136. Okay, 136, and then we run that one. So in other words, so our B1 is going to be 248, and then our B2, it's going to be 252. Let me first check in the chat. Are we on the same page there as we proceed? Are we together? Okay. Let's continue slowly, and then we get to know the difference of what we are doing. Now, if we remember with the marginal tables, we are getting the sums of the different levels within a cross tabulation. If we are considering the row-wise, that is, we are going to put a 1 inside the command. If you're considering column-wise, instead of 1, we put a what? We put a 2. How about in case you want to do, if you want to do, when we go to the percentages, all right? Remember when we are dealing with percentages, we are calculating proportions within a particular table, within a particular cell. In case if you go back briefly, if I take you back to my table, what we are calling a cell, it is that particular count within, in case you're considering, for example, a 2 by 2, each count, it represents a cell. Okay, so now when you come to line 40, and remember how our table looks like, if our table had 1 to 1 count, 1 to 5, 1 to 7, and then 1 to 7. So in case we want to get the percentages for each particular table, for each cell, this one is the grand total. We'll do prop.table, and then inside we put a my table. We put our object name. In that particular case, we'll be coming up with cell percentages. Okay, so when you run line 40, will be having 0.242. This is for the first cell. And then when you come to A1, then A1, B2, it is going to be 0.250. These are just the different percentages that we are getting. But in case now, if we are to consider raw percentages, it implies that now my count is going to be divided by the total amount within that particular row. For example, in A1, if I'm considering the row for the case of raw percentages, it implies that each particular value within a cell, it will be divided by its total marginal value. So the first one is 121, we'll divide it by 264 because that was the total to come up with the raw percentages. Okay, depending on what you want to report. So for the case of the raw percentages, we get each particular cell and we divide it by the raw marginal total. And then if it is the column now, we are going to be dividing by each cell, we divide by the value, the total column value. That is the difference between the raw percentages and then the column percentages. So most of the time, for the case of the cell percentages, you've not differentiated anything. You're just taking the full total of what you're having. But with the raw percentages, you are considering for the case of, for example, in this particular case, which is with two variables, A1 and A2. And then for the case of the column, we'll be getting our count, we divide it by the total value of either B1 and then B2. I don't know if that is clear. I hope that when we use the real example, it will make more sense. Does it sound okay? Okay. All right. Now, what we are going to do, let's use a real example for example, from the data that has been collected and see if it will make, maybe in that particular case, it will come out vividly very well. Now, what I want you to do is that let's import our work salaries data set. Here, I'm setting my working directory, which I already have. Then I want to read work salaries within R. If I run line 65, I'm using an object named salaries. I run line 65 and I check that within my environment, I'm having 397 observation of 6 variables, which we saw within the Excel sheet. You can also click on the Excel icon and then view. We saw with line 66, it can help us to see the structure of the data set. Let me first check in the chart. Have you been able to import the work salaries data set? Have you imported? Okay. All right. Great. I think now at least we know what that means. Okay. So when we look at the STR, the salaries, the structure of salaries, remember salaries is my object. First, we are given our data frame. Okay, that the data set is a data frame with 397 observations and then 6 variables. When you come and check on the rank, it is being seen as a character. So we need to convert this to a factor. The same applies to discipline because we know that disciplines there, it is also a categorical variable. And then sex is, which here R is seeing it as a character. So we need to tell it that convert character to a factor. So my line 69, I'm just going to run that. Hope we all know what it means. Then I run the discipline. I run also the sex. I can now go back and run my structure again. And now from here, I can see that now my rank is a categorical with three levels. Discipline has 2 levels, and then sex has also 2 levels. The rest are just quantitative, they're just numerical. So now let's move on. Okay. Maybe the other thing that I did online, I wanted to see how all these factors influence somebody's salary. And in this case, my salary is continuous. So in this case, it's being read as an integer. We can convert the salary into a categorical variable because we need to cross-tabulate between 2 categorical variables. So if you remember what we did in data manipulation, I can categorize based on the median, based on the mean, depending on whatever that you want. If I run line 978, it gives me a summary statistics of the variable salary, okay, with the minimum, the median, mean, and then the maximum. So when you come to line 80, I said that I want to create a new variable, salary cut, all right, within my salaries data set, and then I use an if-else command. If-else command, I put what inside, I need to put my test. When the test is passed, I put, it will be a yes. When it is not passed, it will be a no. So I considered 13706 as my mean, that in case the test that I've put now is that if my salary is less than the mean, my yes will be the low, otherwise label it high. So I expect that in case I run this particular line, I'll be able to see a new variable that is being created. So if I run line 80, okay, I'll see that for me to view to check if it has been successful, I can click my view, I can type view salaries, and then I'm able now to see. So where I have got low, it implies that that salary is less than the mean. Otherwise, then R has recorded it as high. Okay, now let's go back. So what are we going to do? When remember with the categorical data, we use table as the command, and then we use table as the command, so I can say salaries and rank. I can run that, and then it will tell me that within the rank, I've got 3 levels, the associate professor, which has got 64 as my frequency, then assistant, 67, and then prof as 266. Okay, now I also want to run the one of salary cut, which I've just created. If I use table, it is showing me that the frequency for those that have high salary, it is 168, and then the low salary is 227. So can I find out if there is a relationship between salary and rank? Or on this particular case, it's going to be rank and then salary category, because salary cut is the one that is what? That is categorical. All right. So in case I come down here, for me to do a cross tabulation, if you saw the first example, we had table, and then we had put A and then B. Remember, these are my variables. So instead of putting A and B, what I'm going to do, I'm going to consider my first variable as salaries, go into my salaries data set, get for me rank. And then the other one is salaries, $, salary cut. Both these variables are categorical. Okay, let me check in the chat. Are we on the same page? Are you following what I'm doing? Okay, great. Okay, so if I run, you can also do the same at your end. If I run line 89, I hope you're seeing what we are having. If I run line 89, so it implies that in one of my variable is rank, which rank has 3 levels. And then the other variable is salary category, which has 2 levels. So I have a 3x2 matrix or a 3x2 contingency table. This is micro tabulation. And they're telling, if you can read this out very easily, is that we've got three associate professors that get high salary. Then assistant professor, it is 0, no one gets high salary. And then for the case of a full professor, there are 165 that have high salary. When you come to the low, you can say 61 associate professors get low salary, then 67 assistant professors have got low, and then 101 professors get low salaries. That is how we are reading it. That is our table. Now we are going to take another exam. Assuming that I want to put everything into an object, I'm taking you back to the other example, fifth example that we had. So what about in case I get line 89 and I put it inside an object, my table? So it's going to give me the same result. I run that, and then when I run my table, I'm getting the same. Now, I want to explain the concept of the one of the margin, add margins or the margin tables. This is the concept here, whereby how do we add the margins? For example, in case I want to get the marginal distributions for rank, and then the marginal distributions for salary cut. So this is what I'm having. Inside now, I use the command add margins. After adding margins inside, I put my object, which is my table, and then margin is equal to C inside 1 and 2. 1, these are the rows, and then 2 other columns. I'm telling R that I need the marginal sums for the rank, that is number 1, and then for the columns, for the salary cut, that is the 2. So I'm going to sum the margin sums for both the rows and then the columns. It's what I was explaining earlier in the other example, but hopefully that here it will come out very well. So that is line 94. If I run that, this is what I'm getting. No. Let's complete this part before we get a break. So, if you're seeing the sum now, we are seeing that now the total sum, the marginal distributions, we've got, we shall have 3 plus 61. We are having a total of 64 associate professors and then 266 professors. In case now we sum column-wise, that is the 2. So those that belong within our rank, we've got 168 with high salary and then 229 with low salary. How about the proportions, the prop table, the one that I mentioned, whereby in this side up there I said cell percentages. So we need to get the cell percentages for each. So we use what we call a prop dot table. So when I run this particular line, I'm going to, this is going to be my output. All right. So it is so what we are having here, I'm explaining the cell, how to get the cell percentage. We are taking up everything. So it is going to be here, it will be 3 over the grand total. The grand total, which is 397. These are the total number of observations. So it's going to be the same. Even here, it will be 61 divided by our full total, the grand total. Those are the cell percentages. When you come to the same story here, 0 over the grand total, and then when you come to 165 divided by 397, these are going to be our run by our grand totals. That's going to be our prop dot table. Okay, what about in case of cell percentages? Now, for the case of cell percentages, it is going to be with respect to a particular level. For example, if we are to consider this particular value, if we are now considering row percentages, so it implies that we will be dividing by the total sum, the marginal sum that we got. For example, in this particular case, if we are considering associate professors, 64, 67, 266, these are marginal distributions, the summation of that, the total frequency of that particular level. So in this particular case, if we are to pick the cells, if we are to pick the row percentage, it's going to be 3. I divide by what? By the total. So it is different from the one of the cell percentage. And then here it will be 61, I divide by 64. Those are the row percentages. In case of column percentages, now you divide by the total column marginal value for each respective cell. Let me check in the chat if we are on the same page. Is it clear? Okay. All right. Now let's move on. Let's complete the last part very fast, and then we'll see how to continue. Now, remember my prop, I saw the prop dot table. Then inside I put my what? I put my object. So for me to see if there is if the two variables are dependent or not, I use a chi-square. In R, let's do for only 5 minutes, and then we go for a break, please. We need to complete this part, and then we come back and do the last bit. So we're going to use the chi-square. Let's be a little fast. A chi-square test. So I want to, my first variable is rank, and then the other variable is the salary cut. If I run line 98, okay, can somebody tell me what within our output, we have the Pearson's chi-squared test. We are given our data, we have salaries, we have rank and then salary cut. Our chi-square is 128.62. We've got 2 degrees of freedom. I believe now we know why we have 2. And then we have our p-value as 2.2 times 10 to the power negative 16. Okay, can somebody tell me what conclusion can you come up with depending on the results that we have? Okay. So there is an association between rank and salary cut. Great. So we can conclude that there is what? An association. So from line 98, I can put everything inside my object called test. So here, if I run that same line again, I've not changed anything, and then I type my object test, it will give me a similar output. From there, you can type test, and then you put the statistic. If you put the test statistics, it will give you the chi-square value in case you want to split, but all the values are being, what you need to come up with, the conclusion is being given. If you want to know about the p-value, checking the expected values, the observed, and then the method that is being used. So these other bits also, you can go ahead and check, is there any relationship between sex and salary category? Still, it's a chi-square to tell you that if there is. Another question is there any relationship between discipline and salary category? Let's run line 113 and see where, okay. What answer would you give? Is there any relationship? Is there any association? Okay, yes, there is. That is great. What about line 110? What would you conclude with this particular result that we have? Can you type in the chat? What conclusion can you come up with? Yeah. What conclusion? Can I get more answers? We accept the null hypothesis. Great. That there is no association. In other words, we fail to reject H naught. So, and the rest of the other bits, maybe the last part, it's on line 122. In case you want to consider 3 categorical variables, what do? We still use the same command, my table. We want to check rank, discipline, and then sex. When you run that particular line and run line 1, 2, 3, you can also be able to tell we've grouped according to the disciplines that the associate professors who are doing sciences, we have 4 females and 22 males. Then those that are doing humanities, we've got 6 and then 3, then the males are 32. When you come to the professors that have got humanities as their discipline, there are 8 females, and then we've got 123 males. For the case of those that are doing sciences, we've got 10 females and then 125 males. And then the rest you can practice on your own. Since now we can stop there on the part of the categorical data. Okay. Any question before we go for the break? Kindly share today's material. In this particular case, we are not going to use the Fisher's test because we've not gotten any error when we're using the chi-square. But in case you come across something like that, then you can use the fish exact test. Break time, please. Okay. Okay, let's take a break for 10 minutes and then we'll join again at 4:11. Thank you. Okay, thank you. All right, Welcome back. Now let's get a feel on overview sampling surveys. We're going to be discussing, because I believe that you've also encountered whatever that I'm going to discuss with you. So in case we reach somewhere and I seek for your views, feel free to participate. For those of you that have done sampling surveys, you've gone to the field, you've tried to collect data, and the different experiences. We all go into different experience when you're collecting data. Okay. Now, I want us to just to recap a little bit on what is a population, what is a sample, because sometimes you find that the population is very big and there are some factors that will not allow you to be able to get the whole population. Okay, in terms of time, and then in terms of cost, and you cannot reach everyone unless if you're having a population that is very small, for example, a census, and then you go in and consider every particular individual. So in that case, what we do, we usually consider what we call a sample, and it's a sample. It is just a subset of a population, and in this particular case, when we collect data from a sample using a sample that we picked from a population, we have to ensure that it gives us the similar representation of what a population looks like to avoid bias. So from the collected data of a sample, we go ahead and perform analysis, but at the end of the day, we have to keep in mind the issue of probability. We make an inference from the data we've collected, and it should reflect with the what? With the population. So the circle moves on and on. That is what is happening with the sample surveys. What is your population? What is your sample? etc. So I've already mentioned about population surveys, whereby they used to draw an inference about a population. Okay, maybe there are different things that you really want to draw conclusion on. For example, on maybe if you're dealing in business, about the sales, the income, the behavior, the satisfaction of the people, and so on. So instead of going
Posting. Says you just send me the link to this. You're posting, so you can allow the student. So you give them example.
Right now. Okay, let's continue. So when we move ahead, we think that as far as a good survey is concerned, most of the time it has to really give us a clear representation of what is happening with the underlying population. And most of the time we do it to see that we avoid bias in the selection. So the characteristics that we pick within a sample should be the same characteristics that are within the population of interest or under study, to avoid bias in the selection. And this is being done through a random process to ensure that there is no preference in the treatment of any specific subject that we are considering. Okay, but nevertheless, like we've been hearing the whole of this week with the experimental errors, and then also in surveys we face what we call sampling errors. These are unavoidable. I mean, you cannot dwell with them, because most of the time the point is that not all the elements of the population are selected. So there's a possibility that maybe could be based on what you want to estimate is not exactly of the sample, is not the exact, doesn't exactly match with the population value that we got from the sample. So that discrepancy between the estimated value and the true population value is what we call a sampling error. Okay, though as we move on, we are going to see that most of the time, depending on the literature, we have to ensure that we minimize the sampling error and we make it as small as possible. Most of the literature, like we'll see, they consider it to be a plus or minus 5%. But what we have to note from this particular slide, what we should pick is that it is an avoidable error. Some people call it an acceptable error, and it looks at the difference between what is estimated or what we've computed and the true population values. Okay. There are many factors that influence when you're going to do a sample surveys. Like I mentioned, sometimes it could be due to the funding, due to the timing, but what is most important is that the sampling design that we select should enable us to minimize the sampling errors. From most of the time, like I mentioned, we ensure that we've got a low sampling error, and this could be a plus or minus 5%. And sometimes it is being referred to as the margin of error. When you check in various literature, and also there are already standard estimates that are being put in place when we are determining the sample size and then the margin of error that we can use. Of course, there's a lot of literature out there. Okay, so in case we take this particular example, whereby it's an opinion poll, and it was a survey that reported 29% adults. They were considering that AIDS is an urgent problem, okay? And the margin of error, in this case, it is plus or minus 3%. How was the data collected? It was based on telephone interviews. Remember, we collect data differently. Some use questionnaires, some use telephone interviews, depending on what kind of data that you're collecting. And then also, is it qualitative? Is it quantitative? Are you going to, if it is qualitative, are you going to use the key informant interviews? Are you going to use FD, focus group discussion, etc. But in this particular case, and we're back to the example, we are considering a telephone interview as the method of data collection that was used. And our N is 872 adults. Okay. So what key things should we note from here? We've got the sampling error, which is the same as the margin of error. In this case, they considered plus or minus 3%. We've got our the probability of estimate, which is 29%. Our study population is being shown. We've got the sample size N. This is our sample size, which is 872. Of course, like I mentioned, we cannot go in for a full population. So we pick a sample size that will give us an underlying representation of the population of interest, or the one that we want to consider. Going back to this particular example, we can really see that the outcome is we have a yes. It can be considered that is binary in nature. We have a yes and then a no, okay? Because the question was asking if still HIV is still an urgent problem. So somebody could either say yes or no. And from our outputs in the previous slide, those that responded yes were 29. So that is the probability of those that responded that it was an urgent problem. So it is 0.29, okay? And then, so when you take one minus, then you get the one that responded no to be 0.71%, which is 0.71. We can further go ahead and get out, since we are given N as 872, we can multiply it with the different probabilities and we come up with the different number of respondents. So the output that we got here, it was already something that is condensed from how the work from the data that was collected, and then so this point estimate was just calculated like the way we were having from our frequency table, and then you calculate the relative frequencies, and by the end of the day they came up with this particular conclusion. Okay, so I've talked about, I'm just giving a summary of the other slide that we are having. So the one was yes, they said it was an urgent problem. So it can also be coded like that within a questionnaire, and then 0 as a what? As a no. All right, but now we saw that 29% of the individuals said that it was still an urgent problem. How confident can we be? Okay, so most of the time, when we are trying to check on the degrees of confidence, when you check in most statistical basic statistics books, when you want to construct a 95% confidence interval around our estimate, here our estimate is the 29% that we are having. So, and when you check in most basic statistics books, I guess we've come across this. Our estimate plus or minus z. This is the z.05, and then the standard error of our estimate. So that z.05, we get this particular value from our standard normal tables. So we are trying to, for the case of the 95% confidence interval, the Z value, when you read it all the time, it will be 1.96. You can check these are just standard estimates. When we want to get the standard error, so it is for our estimate, what we've estimated as the point estimate of 29%. It is PQ, the probability of success times failure over N. So we've got the P, we've got the Q, and then the N. We also have our estimate. So it's a matter of fitting everything within this particular expression. And then, so in case you feed everything back, we see that this particular section here, we are having the 0.03. In case you compute it up, it's the one that was represented when they're coming up with a conclusion, and then our estimate of 2.9 of 0.29. So we can be 95% confident that our point estimate of 29 of 0.29 lies between, when you minus, it will be 0.26, and then when you add, it's gonna be 0.32. But what is interesting, maybe something that you can pick from this particular slide, is that we've got this particular N, which is our sample size. So here we can, and these are the P and the Qs, these are the probabilities or proportions that we can pick, and we can also still come up with something that we can calculate our N here, the sample size that was used. Okay, so from what we have, we can conclude that from this particular expression mathematically, we have the estimate, and then you have a plus or minus the margin of error. Remember, with the margin of error, it's what we also, it's what you can also term as the sampling error. All right. Okay. On this particular bit from the example that we had, if I only pick the part of the margin of error, which was given to us as 0.03, I'm saying that you can manipulate this particular expression and come up with N, because we just feed into these particular values, and then we made the N the subject, the 872, which is your N here. So implying that in case you feed in these particular values, we know this is our Z value, considering the 95% confidence interval. However, you can also go ahead and consider different interval. If you don't want 95%, you can consider 90, 99, etc., whatever that you want. And even if when you go to R, you can adjust the default value to any confidence interval that you want. We have the D. Okay, most of the time the literature want to get a 50-50 plus or minus 5%, and then these are proportions, probability of success, and then the one of failure. So if you've been very keen most of the time still in literature, we can use this particular formula to calculate our sample size, provided we know the P and we know the what? We know the Q. Okay. So, so in this particular example, for example, in case we know our estimated value for P, all right? All we need to know is now we can estimate the required sample size given we've specified the margin of error. Like I mentioned in literature, most studies they use plus or minus 5%, but in the you can also go ahead and use the one that is lower. We always want to use a small sampling error. And then you can also be able to play around and check how to determine whether in case you need a large sample or when you need a small sample. But from what I've just illustrated here, this is a formula for a sample size in case of proportions. And the point is, if you have an estimated value of P, okay, that is the probability of success, and then you can be able to get the failure and compute your sample size. Okay. All right. Some questions that you can explore in case you want to find out your sample size. You can ask yourself, like, what is your target population? Most of the time, if you're going to carry out a particular research, and if you want to do a survey, what is going to be your target population? Are you going to use, for example, are you going to use maybe students at a university? Are you going to consider all the students within a university? Then what is going to be your sample size, or the sample population that you're going to pick, given that you cannot consider everyone? And how are you going to reach these particular people that you want to do research on? Okay. And all those things, you have to ensure that how reliable are the estimates that you're going to use, and also the precision of the estimates that you want to use. How much confidence could you put? For example, we talked about the 95% confident, and then are you sure that the sample size that you're going to use clearly depict the population that you're having in mind? All these are the questions that you need to explore as you're going to go ahead to determine your sample size. All right. There's also what we call types of survey designs. I don't know if you've come across them. Of course, there are very many, but the common one, we have the cross-sectional surveys and then longitudinal surveys. So can somebody type for me in the chat, when they talk about cross-sectional surveys, what comes at the back of your mind? Cross-sectional surveys, anybody who has done a cross-sectional survey to tell us what it is? Okay, one-time sample collection, time series data. And are you sure of what you're telling us? Cross-section is one time off. Okay, prevalence. Collection in one area, data is observed in a fixed period of time. All right. Data collected once. Great. All right. Okay. So just supplementing on what you've shared, when we come to cross-sectional surveys, this is just data that is collected at a point of time. Let's take an example. Maybe you want to collect data on performance of university students, all right? And you set up your research objective, and then you move out to collect your data. After collecting your data, do the analysis, then come up with your conclusion. That is an example of a cross-sectional data. You just conduct it at just one point, and that is the end. You come up with your conclusion, either you're answering your objective or you want to inform policy, whatever it is. So that is those are cross-sectional surveys. What about longitudinal surveys? Somebody to tell us what longitudinal surveys are before we go into the different groups that we can consider. Longitudinal. Yes, I'm reading the comments in the chat, and they're okay about the cross-sectional. Thanks for contributing. And then longitudinal, somebody's asking for a registration link. I'm asking longitudinal surveys. Okay, data collection on a sample at different points in time. Great. Using repeated observation of the same variable. Okay, collecting data at different times. Great. Data from a period of time. used for same individuals or units repeatedly over an extended period, long term. Great. Okay. I'm still going to supplement from what you've shared. When we come, so we see that with longitudinal surveys, this is just data that's collected over time, repeated number of times. And it could be trend, it could be a cohort, it could be a panel. Under the trend, we are considering the same population at different time points. Okay, the sample population at different time points. For example, maybe you're considering if you're talking about the different rains, if we talk about collecting different samples of rains at a given on given times, that is trend. You want to see how cells, the different cells, how cells are performing over time. That would be trends. And under the trends, most of the time, if you hear about time series analysis, that's when we apply the trend kinds of surveys. And then when it comes to cohort, we are studying the same population each time over a given period. An example you can take here, let's assume we've got students that have reported within the university, all right? And then they've reported in the first year, and you want to study their performance until third year. So in that case, that is going to be a cohort. You're using same students. For example, maybe the ones in first year, and then you go ahead and see them in second year, and then the third year. So that is our same population over time, and so it is a cohort. And then when it comes for a case of the panel, if you're considering a panel, here we are studying a sample of respondents, okay? You're looking at a particular person or a particular household. For example, if you're looking at, maybe let's take an example of a child growth. You're looking at this same child and see how they are growing over time. Okay. All right. So we have different sampling procedures. All right. We have what we call the non-probability sampling, and then we have the probability sampling. So, and still within this particular, these two types, they are distributed. Under the probability sampling, we have the simple, systematic, stratified, cluster. Of all this, they form a multi-stage sampling. We have the non-probability sampling, where we have, you can have conveniency, purposive, snowball, etc. So we're going to go ahead now and discuss each together and see what it implies, and then I'll be supplementing. Okay, I've talked about this particular slide, so we are going to skip it. There are different advantages of using the probability sample, and then also the disadvantages of using a non-probability sample. Okay, so I'm going also to go ahead with that. So let's move on now to methods in sample surveys. Let me ask in the chat, what is simple random sampling? This is one of the method of probability of a probability sample type. What is simple random sampling? Can somebody type in the chat? We are discussing the first one, simple random sampling. In case somebody has collected a survey, equal chances of selection into the sample, selecting samples randomly. Every event has an equal chance of being selected. Wow, wonderful. So ensuring that each sample has an equal probability of being selected into a sample. I'm just reading your comments, and they are all interesting. We are saying that, just speaking from the, selecting sample based on equal probability, each element. Anyway, the point is that in this particular case, when we talk about simple random sampling, the whole thing is that there is randomization. There's a randomization process in all. But what we do is that there is each element has an equal probability of being selected from a list of all the population units, like some of you have contributed. So the point is that each element has an equal chance or an equal probability of being selected to form from a population unit to form our sample. And most of the time we donate sample as N, and then small n, and then population as capital N. In other words, there is no preferential treatment during the selection. Okay. All right. Now let's discuss about the second one, which is systematic sampling. Can you type in the chat what is systematic sampling? Thank you for the responses. I'm reading them in the chat. In simple random sampling, there is an equal chance of being selected. Yes. So you randomly select and everyone has the same chance of being selected. So now we are defining systematic sampling. Susie, what you're sharing is not right. Sequential selection. Elements are selected at a regular intervals using a predetermined pattern. I agree with you. Then at every interval, you select an item randomly following a sequence, selecting participants at regular intervals. And then I'm going to read only the last one. Starts with a number selected randomly, and then a sample selected at a regular interval. Wonderful. Okay. Now let's move on with the systematic sampling. So we are saying that, like some of you have shared, it is also another method of random sampling. But what is so special with this one, with the systematic method, like you've mentioned, is that there is a certain criteria that is followed, whereby the first unit is selected at random, okay? And then after that, a predetermined pattern is followed. How do we determine this particular pattern? If we are saying that the first unit is determined, we follow what we call a sampling interval. And the sampling interval, for example, in case I can say, if I denote it as K, this one is always equal to N, my population, over the small n, that is the sample size, to give me, to be able to give me the sampling interval that I'm going to take. And most of the time, when, for example, maybe you want to do you want to sample, for example, let's say you've got a particular list of your students, let's say 100 of them, and you want to know, okay, how many can you consider in your particular study, and you want to use a systematic sampling. So it is up to you. You can determine, well, from my list, if I've got 1 to 100, you can pick randomly any first person that you want to consider. But now for you to come up with the interval that you're going to consider, you get the total n, and then you divide it by a small n, depending on your n, and then you divide by a small n, which is your sample size. Okay, let's take this particular example here. If my n is 100, capital N is 100, and my small n is 10, for me to come up with a sampling interval, it's going to be 100. I divide by 10, and then this one is going to give me, it will give me my K as 10. So it implies that between 1 and 10, I can choose any person to start with. And then after that, I'll go on picking every 10th person to include in my sample. So in this particular case, if, for example, if I pick the 7th one, then I count up to the 10th person. This person is included in my sample. So 17th, the 27th, up to the 97th. depending on now those people that you'll be circling, they are the ones that you'll be including in what? In your sample. Maybe you can ask yourself that, what about in case I'm not coming up with an integer? Most of the time what happens is that you round off to the nearest, either below or above. It doesn't matter. Still, most of the time you stay into that particular, the range that you want. Let's consider, for example, if you want your small n to be 175 and your capital N, the population is 1,000. And when we first here, when you see the sampling interval, when you divide out, it's going to be 5.71. Okay, so they are either when you round, when you can take 5, or you can round off to 6. If you consider 5, you're going to use 200. If you consider 6, you're going to use 167 as your sample size that you're going to consider in the study. Okay. And then also, you can also ask yourself is that when do we use the systematic sampling? All right. One of the reasons could be in case you're having a small population and when the list that you want to use is roughly of a random order, and when the list of the population does not exist. It is most time referred over the simple random sampling because, I mean, it is easy to measure. You can easily form your framework and then be able to include people within your sample. Okay, this is just an example that we can consider, but also we have this particular example that we can put up back of mind. Here we're having a frame, our N is 100, and then what if we want our sample size to be 20? So it implies that my sampling interval is going to be 100 by 20, and I end up with 5. Okay, that is my sampling interval. So it implies that I can choose my first unit between 1 and 5, 1 and K. Okay, so because my K, remember, it's N over capital N over small n. So after choosing the first sample, then I'm going to pick every 50th person. So from 4, I'll count, then whoever falls in the 50th position will be included within my sample. And then later I'll be able to get these people that within this particular those positions, the ones that I will take and include to act as my sample size, which is of 20 in this particular case. So the blues are the ones that are picked. For example, you start from 4, you count 1, 2, 3, 4, 5. So 9 falls in the 5th position, and then you pick up that particular person. You can also use this kind of sampling, maybe, for example, in a hospital setting, and you're counting the number of patients that are coming in, and you're like, oh, well, I'll consider patient after every 3rd person. So you randomly choose the first one, and then you count the one that takes a 3rd position, you take up that person. Okay, now let's move on to this other one, which is stratified sampling. Can we define stratified sampling? Jen is saying grouping elements in small groups called strata based on some characteristics. Thank you, Cloud. Any other person? Stratify. From stratify, you're portioning data, just giving a hint. You strata internally, great. Then grouping elements into non-overlapping groups. Yeah, Martin, you're right. Then they are in terms of strata or layers. That's great. Selection following categorization. All right. Then, what? Okay. Okay, so just To supplement on what you've shared with stratified sampling, we said that in this case, you're partitioning into groups, which are called strata, and then sampling is performed separately within each stratum, okay? And they're not supposed to be overlapping, as a colleague has shared, all right? So there is no issue of overlapping. The stratum has to be mutually exclusive. For example, you can consider urban and then rural areas. Then you can also consider, maybe you want to look at economic categories, putting them into different groups, geographical regions, etc. Within the stratum, they have to be homogeneous, but across the stratum, they have to be heterogeneous. Those are some of the characteristics that we can pick. Okay, then with the clusters, remember with the stratum, in that particular case, we are partitioning into groups. But when it comes to a cluster, in this particular case, we are taking the whole group, the group of the population elements. So the whole group acts as our sampling unit, not as a single element like what we saw in the stratified. So the clusters in this particular case are our first sampling units, what we choose out to consider. Okay. So an example, you can take maybe your clusters, you've got maybe 10 schools, and then you only choose to consider 3 schools to include in your study. But also these schools that you choose, they have to have similar characteristics of have to have similar characteristics across the same schools that you're going to study of interest. We have the multi-stage sampling. Under the multi-stage sampling, this one considers all the other sampling that we've talked about, the different stages. So you can do everything at a go. You can stratify. After stratifying, you do cluster sampling. Then from cluster sampling, you go ahead and do systematic sampling. So all these, they form what we call multi-stage sampling. And most of the time they are done at usually national level surveys. They perform them using a multi-stage sampling. And within this particular design, I'm saying that you can include the different sampling procedures of interest that you want to consider. This is also another example which has you can move from the districts, you got the villages, and then until you go to the household level. But at these different levels, you can combine the different sampling procedures, the systematic, the stratified, and then the cluster. They all come up and form what we call a multi-stage sampling. Okay, so what I'm going to do, I'm going to stop here, given that we have little time left, but I encourage you we've got some work that is left that for you to go ahead and read. At the same time, I would encourage you to run the R script, which has got how to come up with a sample size. They are not hard commands, given that now you have a background of R. The moment you go and run the sample size.R script, it should be very easy for you to understand. And then make use of the notes. We are not going to take down the materials now from the Google link. So try to get back and also practice throughout. Professor Susan, I'm going back to you.
The link, where is the link? Okay, ladies and gentlemen, thank you so much for being patient for the 5 days. We have a survey that has been posted in the chat. Please fill in the survey for the next 5 minutes. And then after 5 minutes, we are going to forum to close. So the forms, the survey is being posted in the chat. Thank you very much. Hello? Yes. Good evening, all. Mm.
I can see the number is reducing. I hope the people are filling in the survey which was shared. And while we continue to fill in the survey, I think Professor Rogerio is still in our midst. I would like to hand over for him to use this opportunity so that he can also give the closing remarks. Professor Rogerio? Okay, ladies and gentlemen, once again, thank you so much for making it to the last day of the training. For today, we have another training coming up. I'm sure you have registered. I just hope that you look it up on the same advert. I think it will be after next week, if I'm not mistaken. So please, thank you so much for being very engaging and for joining in to participate on this. I would like to thank our facilitators so much for taking us through. Thank you so much, Professor Susan. Thank you so much, Dr. Odong and Dr. Namaweji. Thank you very much. Thank you so much for being wonderful, great teachers again. And we definitely will see you again in our next training when it comes up. Thank you so much.